Dear students, today we'll be discussing the spiral motion of charged particles under the effect magnetic effect of the magnetic field. And how is this possible? How do we give effect to a spiral motion? We will be seeing it with a example which is drawn from the uh, concept of cyclotron. So what is a cyclotron? Cyclotron is a particle accelerator. This is known as the particle accelerator. So using a particle accelerator, we increase the speed of the very tiny particles such as the proton, neutron, electron, etc. Not electron, in fact, the more massive particles such as proton, neutron to great speeds, which does reach close to the speed of light. C is how much? C is equal to 3 into 10 to the power of 8 meter per second. So this sort of speed is reached in the particle accelerator, and then it is smashed with another particle so as to draw the conclusion regarding the constituent particles or subatomic particles of the more massive particles. Okay, so in fact it is a study of the constituent subatomic particles of which the bigger particle or a more massive particle is constituted. Okay, so this type of studies was done in the previous time using cyclotrons, and a more what you call advanced version of cyclotron is synchrocyclotron. So let us see this particle accelerator and what does it constitute. So I have drawn a diagram wherein the cyclotron consists of two Ds. These are the upper surface area looks like D, and another D which is separated by a very small distance. And what we do is that we exert a magnetic field, or we create a magnetic field in the plane which is perpendicular to the D. Okay, so we have a B vector like this, and the particles, let's say, are shot with an initial speed perpendicular to the boundary of the D into the magnetic field region. Okay, and as we know from our various derivations regarding the charged particle motion under a magnetic field, we have R is equal to mv by qb. This is one sort of relationship where we have seen that the radius of the circle executed by a charged particle moving in a field which is perpendicular to the initial velocity. So we have seen those things in great detail. So the expression for radius is R is equal to mv divided by qb, where m is the mass of the charged particle, v is the velocity of the charged particle, q is the charge, and b is the magnetic field in which it is moving. So this is the expression for R. Another expression that we had found from here, V by R, as we know, this is equal to omega. So V upon R is equal to QB by M. And furthermore, we had seen, since this is a uniform circular motion, therefore omega is constant, we can write 2 pi by T, where T is the time period. And this we had seen as QB by M. So time period, it is given by 2 pi M divided by QB. So one thing that I had mentioned while deriving this thing is it is independent of velocity. No matter what the velocity is, time period always remains the same provided the particle mass, charge, and the magnetic field in which it moves does not change. So then the time period remains the same. So herein also we will make use of this fact. So what we do is that a charged particle, when it is projected with a speed, initial speed, let's say v, from the boundary of the D into the D. Okay, so what does happen over here is, okay, so this is this similar structure is also built above it. Okay, so A similar structure exists over here also. Similar structure, exactly a replica of it is built above it, and the field is in the vertical direction like this. Okay, so B is like this, and in the space in between the two D's, which is kept above each other, the motion of the charged particle takes place within this region. Okay, so we have this gap. Okay, so this is just like a circular sort of D, which is separated by a small gap over here, and a similar structure like this exists exactly on top of it, and a magnetic field is present in between the gap. So the motion of the charged particle takes place over here. Okay, so this is a 2D picture. I hope matters are more clear with this 2D picture. Now let's move on to the actual experiment. That is, if it is projected with velocity v from the boundary and it moves in a circle, r is equal to mv by qb. So when it reaches the half circle and it enters into the gap between the two D's, okay, so this is the gap, okay, where no material exists. That is, these two are magnets. Above and below we have two D-shaped magnets placed one over the other. This is, supposing it is this north pole and this is south pole. So we have a very powerful magnet which is kept one above the other, and the motion of the charged particle takes place in the gap in between the two. So when it reaches this particular region, then what we do is that this is devoid of any magnetic field. Okay, so we do not have any magnetic field existing over here. The reason being that this is a magnet and this is a magnet, so the magnetic field will be generated in between the surface of the magnets, and the gap which exists in between is devoid of any magnetic field. So when it reaches over here, the particle which is projected from here, it reaches at this point. When it crosses the region, it is provided an electrical stimulus. That is, for a short duration of time, an electric impulse is created which accelerates the particle through the gap, and when it reaches over here, it has a different velocity. So with this increased velocity, the radius will also be different. So it executes not this particular circle, but it executes a bigger circle. Again, when it reaches this particular point, an electrical stimulus is provided, which again increases its speed. When it enters the next half of the D, it has a greater speed, and with that speed it has even a greater radius, and again it changes its radius to a newer value. So each time the radius increases with the increase in the v. We keep on increasing the velocity like this by providing short stimulus of electrostatic field in between the gaps of the D, and by continuously doing this, now this D is of a very large magnitude. Okay, so spanning over, let's say, half a kilometer. So by doing this continuously, we can reach close to the speed of light, let's say 0.9 c, 0.98 c. So very close to the speed of light, and then it is smashed. Okay, so when it comes out of the D during its last leg of the spiral motion, it comes out, and then this is shot into a tube where various other particles are released, and it smashes onto them, and the newer particles are generated, and we study those particles and draw a conclusion regarding the constituent subatomic particles which make up the parent or the original particle. So this is the idea of the cyclotron, and this is a spiral motion. As we have seen, T is equal to 2 pi m by qb. So upon each increase in the velocity upon completion of half a time period, we see that the time period does not change. Reason being, we are increasing the velocity, but since t is independent of velocity, therefore the half time period, that is t by 2, does not change, which is pi m by qb. So this does not change. Okay, therefore what advantage do we have is that we set a electrical device over here such that exactly after t by 2 time a short impulse is provided to the particle. So when we set this particular time, each half circle we give a short electrical impulse, and this pushes the particle or accelerates the particle through the gap, and it has increased velocity. So this is the advantage of the the circular motion, and using this charged particle producing a circular motion when kept in a magnetic field perpendicular, we can produce a device like this, which is used, as we had said, for the study of the subatomic particles. So I hope this becomes clear, and this is indeed a spiral motion. Now, students, we have discussed the spiral motion. In the next lecture, we will be discussing the helical motion.